Welcome back everybody to another lecture video. In this chapter we're going to be looking at hydrocarbons. So let's just get started. The learning goal in this chapter is going to be to identify properties of both the organic and inorganic. So that's the goal. So we'll spend a little bit of time looking at the differences in properties between the organic and the inorganic compounds. Now, organic chemistry is the study of carbon compounds. Organic chemistry means that they have carbon in them. So that's where you got to be careful when you're buying products that say organic. All that really technically has to mean is that it contains carbon. So organic compounds are carbon containing. Such as vegetable oil. Vegetable oil contains carbon and hydrogens, and these are not soluble in water. Not the atoms, not carbon and hydrogen, but oils in general. Let's say this is veg oil, and you can see that they're not soluble in water. And so one of the properties already is going to be something like solubility. Do things dissolve? So you've already learned a little bit about what the state of dissolving is for an oil. Now, an organic compound will always contain carbon and hydrogen atoms. They may also contain other nonmetals. These include atoms like oxygen, sulfur, nitrogen, phosphorus, or halogens like fluorine, chlorine, bromine. This is just to name a few, but they're going to be nonmetals. And organic compounds are often found in products such as gasoline, medicines. I guess I could write a couple of those. Gasoline, medicines, shampoos, plastics, perfumes, and so on. Now we organize organic compounds by something called their functional group. We can say it's functional grouping. And compounds that contain the same functional groups will have the same physical and chemical properties. So we'll talk about functional groups here in a little bit. Let's talk about the difference between intermolecular forces and intramolecular forces. So intramolecular means between atoms in a compound. So this means that we're going to be talking about covalent bonds, right? Sharing of electrons within an atom. Now, covalent bonds are different from ionic. Let's talk about a little bit of the difference. Metals and nonmetals, with them having a big difference in their electronegativity or in their charge, these end up doing electron transfers, where the metal will transfer its electron to the nonmetal. This will give each ion or each atom a charge, turning it into an ion. So this is where ions come from. Ions means ionic. So the sharing of electrons doesn't take place, the transfer takes place. That's what ions are. Now, nonmetals and other nonmetals will share electrons. And electron sharing is what we call covalent. This equals a covalent bond. So that's just the difference between the types of bonding. Now, intramolecular forces, again, between those atoms in a compound, will be either covalent if they are between nonmetals, or it'll be ionic if they're between metals and nonmetals. But those are the two types of forces, covalent and ionic, and they are going to be intramolecular. Now, intermolecular, this is between free atoms. Or molecules, free atoms or molecules. So floating around in space now, we've got molecules that are not attached, or atoms or molecules that are not attached to each other. Now these follow a different set of forces. Where we had covalent and ionic for intramolecular, here we have intermolecular forces such as the dispersion force, which is weaker than dipole forces, which is weaker than hydrogen bonding, which is weaker than ion dipole forces. Now, if you don't remember these, you've got to go back and read some of your Gen Chem. This understanding the differences in these forces will help to understand some of the differences that we see in our physical properties. But what we want to say here is that whichever of these forces that you ultimately have, your intermolecular forces, the more that they are, or the stronger, more or stronger forces equals a higher melting point or a boiling point if we are comparing them. These forces here are the reasons that solids and liquids actually exist. If there were no intermolecular forces, everything would just be a gas. All atoms and molecules would just be floating around, not interacting with each other. So we're pretty lucky we have intermolecular forces at all. Now again, properties of organic compounds. So organic compounds will typically have covalent bonds. They're typically going to have low melting and boiling points. They're typically going to be flammable. That means that they can catch on fire and undergo combustion. So flammable, and they can burn. They're usually not soluble. I'll write insoluble in water. Now we compare these to inorganic compounds. So you can kind of put that up here, versus inorganic. Now inorganic would be non-carbon containing. Those would tend to have, since they have metals in them, more of a ionic bonding instead of covalent. They might tend to have more or higher melting points and boiling points. They would be not flammable, and they wouldn't burn, and they would also be soluble in water. So our organic and inorganic are going to have kind of opposite characteristics. Now vegetable oil, again, is a mixture of organic compounds. It's not soluble in water, and you can see here things that aren't soluble in water tend to form layers or not mix very well. Here's a table of some properties you guys can use to help with your first lab. Some of the questions in the lab ask about this. But you can see some of what we've talked about here just sort of visually shown. So organic versus inorganic. You can see types of atoms they contain. Na is a metal, whereas CH there's no metals. Bonding, see covalent versus ionic. The melting points you can see for this organic compound, it's very, very low, and it's very, very high for the inorganic compound. But anyways, this should give you an idea how those compare a little bit. All right, now quick test for you guys. So go ahead and pause it and give it a shot. You're deciding if it's organic or inorganic. And hopefully you got all of those correct. Again, A and D are both inorganic because one contains a metal and one has a high melting point. Those don't jive with organic. Representations of carbon compounds can be different. Hydrocarbons, as we call them, hydrocarbons are organic compounds that contain only carbon and hydrogen, hence the word hydrocarbon. So hydrocarbons only have C's and H's. In organic molecules, every carbon has 4 bonds. In methane, CH4, The carbon atom forms an octet by sharing its 4 valence electrons with 4 hydrogen atoms, right? Carbon has 4 valence electrons. Hydrogens each have 1 valence electron. So they share those 2 electrons to make covalent bonds, and carbon ends up with a total of 8 electrons. Excuse me. So we have a few different representations. We have a 3-dimensional and a 2-dimensional representation of methane here to look at. So the space-filling model and the ball and stick model are 3-dimensional models. The wedge dash model is 2D, but the wedges and the dashes imply 3 dimensions. The dashes go back into the board. The wedges come out of the board. So we're supposed to picture the 3D space there. The expanded structural formula shows the carbon with all of the covalent bonds, and then the condensed formula just doesn't show the bonds, it shows how many atoms are on those particular carbons. So these are the different representations. We'll use most of them. Now structures often, or structures are most often represented using their corresponding 2-dimensional formulas, the expanded and the condensed. So I just wanted to kind of show those again here in a little bit of a bigger context. I'll draw another one for you. Let's do a 2-carbon compound. So 2 carbons, now both carbons are still going to have 4 bonds apiece, and if it's a hydrocarbon, then they only have hydrogens. So all of our carbons have 4 bonds. Now if we were to take this condensed structure from this expanded structure, we would just take this carbon has 3 H's on it, so CH3, and then this carbon has 3 H's on it, so another CH3, and there we go. So condensed, expanded. Expanded just shows all the lines to all of the hydrogens. Now, again, using methane, carbon forms 4 covalent bonds to hydrogen. Now, methane is what we call tetrahedral. It's got 109 degree, it's written here, 109 degree separation between each of the atoms. So the bond angles are 109. This is going to be the case for a tetrahedrally bonded organic compound. And we're going to see that there are a couple of different orientations that we'll get using our carbons. When carbon has 4 bonds, it's got 109 degrees, but sometimes our carbons will only have 3 different bonds, or 3 bonds to different atoms, which will give us a trigonal planar configuration. Now, all the hydrocarbons can be referred to as either saturated or unsaturated. So I just want to mention that term real quick. A saturated hydrocarbon is one where all of the bonds are single. So only single bonds. All right, ethane. So ethane I drew for you. In ethane, we have 2 carbons and more hydrogens. So each of the tetrahedral carbon atoms will form 3 covalent bonds to a hydrogen and then 1 more to an additional carbon. So again, space-filling model, ball and stick model. We've got the 2D model here, wedge and dash, expanded and condensed. These are the ones we're going to focus on the most. I'm not even showing you line angle yet. We have one other called line angle. But this is how we represent our hydrocarbons. All right. So your job here in this one is just to predict the shape around each of these 4 carbon atoms. You're going to say whether or not you think this is a tetrahedral or trigonoplanar or linear, or, predict the shape. Give it a shot. So if you notice that they were all single bonds, then that leads us to know that there has to be a tetrahedral shape. There's a 109 degree bond separation between all of those atoms. All right, so organic compounds, check. Alkanes. Now, a large number of carbon compounds are possible because the covalent bonds between carbon atoms. Um, uh, these are very, very strong, and they allow long chains and long stable chains and long branched chains to form. So that gives lots of different possibilities for compounds. So the learning goal of this chapter is, or this section, is to be able to write IUPAC names and to draw condensed structural and line angle formulas for the alkanes and cycloalkanes. So let's give that a shot. So alkanes are formed by continuous chains of carbon atoms. They're named using an IUPAC system. They have names that end in ane, A-N-E, and they use Greek prefixes to name the carbon chains with 5 or more carbon atoms. What does that mean? Here's an example. So for the first 4 carbon chains, we use these certain, I guess what the word I'm looking for is they're not prequels, what are they? Prefixes, there we go. We use meth for 1, we use eth for 2, we use prop for 3, and we use bute for 4, as opposed to mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, right? So Greek after number 4. So pent, hex, hept, those prefixes you need to know. You only need to know up to a 10. And then the ending for all alkanes is ane. So we put the A-N-E ending at the end. So we need to A, know how many carbons we have, and B, we can name it. So what do we see here? We're looking at a couple of things. We're seeing the first 10 hydrocarbons. We're seeing their molecular formulas here. So you should be able to see that the number of carbons and hydrogens increases. You can see the growing chain here. Each one of these will always have an additional CH group. And then the line angle structure. These are the most interesting ones. We're going to show those here in a second. So, condensed versus expanded. Anytime you are converting between the two, if you have a carbon on the end of a chain, it's always going to have 3 hydrogens on it. So you just condense that to a CH3. All the internal carbons in a chain, right, because there's more chain in both directions, they always have 2 hydrogens. So you can just condense those to be CH2. A line angle formula represents that as well. So with our line angle formula here, we can call this a zigzag, we can call this a line angle. The point here is that each carbon atom is represented. The ends and the corners are carbon atoms. Okay? So this one has how many carbon atoms in it? 1, 2, 3, 4, 5, 6. 6 is hex. This is hexane. All right. So at the end, we already saw from the expanded and the condensed, the ends are always CH3s, and the middles are always CH2s. Well, that's what's happening here too. This is a CH3, and this is a CH3, because they are on the end. Everything else is a CH2. The hydrogens here are implied. Since we know hydrocarbons have carbons and hydrogens, and we know all the bonds are single, it's easier to draw a zigzag and have it represent hexane than to draw out 6 carbons with a bunch of H's, or even worse, draw out the expanded formula. So line angle formulas are really convenient. We'll start drawing them. Let's draw the expanded, condensed, and line angle formula for pentane. So the first thing that I want to do is just draw the carbon chain, right? Pentane. Well, I guess you should go and figure out how many carbons it is. Once you figure out that it's 5, you should start by just connecting 5 carbons. So there's our chain. So we've got 5 carbons. Now, let's draw the expanded formula for that. Expanded just means we're going to stick some lines on this guy and put some hydrogens all over it. Very tedious. This is the same thing, and I've been doing it for decades. Okay. So here's our expanded. If we want to go from expanded to condensed, all we have to do is take the ends, turn them into CH3s, take the middles, turn them into CH4s. So we can count as well, right? This is a C with 3 H's on it, so that's a CH3. This is a C with 2 H's on it, so it's a CH2. There we go. There's our condensed. Now we want to get the line angle. So every carbon is going to be either the end or a corner. There we go. So as long as I have 1, 2, 3, 4, 5 ends or corners, then I can do the line angle. There we go. So that should be how to draw the expanded, condensed, and line angle for a simple alkane. Now, carbon atoms in a chain are connected by C-C bonds. Now, these can rotate. These can rotate along with C-C bonds, and they can have different arrangements. So let me show you what I mean. So in the expanded formula, right, we typically would draw that one way. Angle formula, these are all butane, by the way, 4 carbons. But look at the condensed structural formulas. Because of the way that these can rotate, this structure right here can turn into this structure right here by rotating that angle, and then rotating this angle. Wait, did that happen? No, maybe not. Maybe it was just one rotation. Okay. Every one of these is still butane. That's my point. 4 carbons in a row. Doesn't matter if it looks like a little chain, if it's straight up and down versus straight sideways, if it bends like a U or makes like a Z shape or looks like an L. There's 4 carbons in a row in every single one of these. There's only hydrogens. They're all butane. Drawing it this way does not make this one a different type of butane. These are all drawings of butane. So that's one of the things you need to be vigilant about, is when you're drawing these structures, don't be confused by your own structures or by the way you draw them or the way someone else draws them. Count the carbons. That's how you'll know. Let's talk about cycloalkanes. Cycloalkanes are cyclic. They have 2 fewer hydrogens. I'll put -2 hydrogens. Because the 2 ends that normally would have had 3 hydrogens on them now have a line connecting the carbons, so we can't have as many hydrogens, right? So you should hopefully be able to see that. So propane was C3H8. Cyclopropane will be C3H6. So just by looking at the number, you can actually tell whether it's cyclic or not. By the way, regular alkanes will have a formula of CnH2n plus 2. So however number of carbons you should have 2 times that plus 2. So with propane, right, 3 carbons, so that would be 6 hydrogens plus 2, 8 hydrogens, according to the formula. So just looking at the formula, you can tell if you have an alkane versus a cycloalkane versus a alkene when we get to that. They're named by using the prefix cyclo before the regular name that we would give them based on how many carbons they have. So since this has 3 carbons, it's propane, so cyclopropane. Cyclopropane is the smallest one that you can have. You need to have at least 3 carbons to make a circle or a ring. So cyclopropane, cyclobutane, cyclopentane, cyclohexane are shown here. Condensed structural formulas look just like they were in the open chain forms, but now they're just closed. You can see that we try to draw them symmetrically. The line angle formulas are nice too. Every corner is a CH2. That's the way it goes. So, common cycloalkanes. So try to name these two structures. Again, count the carbons, and then give it a shot. So pause it, give it a shot. So, octane for the top molecule, and cyclopentane, 5 carbons, for the bottom one. We've got 4 problems here, so pause it, give it a shot. So we've got butane, we've got cyclopropane, we've got another octane, and this time a cyclohexane. So this should be giving you practice on counting carbons using those prefixes, the 4 prefixes plus the Greek prefixes, and again, interchanging between looking at line angle and condensed structure. Good. Let's talk about alkanes with substituents. Now, when an alkane has 4 or more carbon atoms, the atoms can be arranged so that a side group, called a branch or a substituent, is attached to a carbon chain. So the learning goal in this chapter is to write IUPAC names for alkanes with substituents and to draw their condensed structural and line angle formulas. So check this out. Both of these are C4. So they're butanes, right? Or they could be. We could name them as a butane, but we'll see that isn't going to be the case here. But there's 4 carbons. 4 times 2 plus 2 is 10, so H10. That's the formula for both of these compounds, yet you can see that there's actually 2 different compounds here. And that's because instead of putting all the carbons in a row, and this only happens when you have 4 or more carbons, if you have 3 carbons, there's no other way to put them than in a row. But if you have 4 carbons, instead of putting that 4th carbon on the end, you could put it on the middle carbon and get a branch. So that's what happens. When you get to 4 carbons or more, we start to get branching that's possible. Okay, so structural isomers are what they're called. Structural isomers have the same molecular formula. In this case, C4H10. But they have different ways in which their atoms are connected. So butane, C4H10, can have this straight chain or branched chain configurations. Now, let's draw 3 possible isomers for pentane. Okay? Or actually, this is for you guys to do. So I want you to take pentane, I'll give you or you have the formula, C5H12, connect it in different ways. Go for it. You may or may not have come up with more than 2 ways. Hopefully you started by just putting them all in a row. And then what you should do is you should shorten your branch by 1. So put 4 carbons in a row, and then stick that 5th carbon somewhere different. The only 2 options that you would have had is to stick it on the 2nd or the 3rd. Notice that if you had stuck it down here, as opposed to up here, it would have been the same exact molecule. It just would have been upside down. So that is technically not a different option. Doing this is not different than doing this. If I turn this upside down, it just becomes that. And then you could also put the 4th and 5th carbon on the 3rd carbon, right? You could do a 3 carbon chain and then just stick 2 groups on that middle carbon. So you could actually get 3 different structures with pentane. You can't get cyclopentane, though, you'll notice, because you've got too many hydrogens. So these are structural isomers. Part of your task is to be able to spot whether 2 compounds are structural isomers or not. That means they have the same formula, but they're arranged different in space. Just to go back real quick and ask you kind of a test question, not a test question, a sample, a practice question. Oh my God. Okay, here's my question. How many of these are structural isomers? You should have already said none, right? Because they're all the same formula. There's nothing different about any of these. And if you don't remember why that's the case, even though they all look different, then you need to worry more about structural isomers. But these are not structural isomers. Those are the same compound. Structural isomers have the same formula but are different looking. Those were different looking, but they were connected exactly the same. These are all connected different. What's happening? Do what I want, pen. Wow. Okay. Sorry about that. Pen problems. Substituents in alkanes can either be, carbon groups that are attached to not ends of a chain, but they can also be other things. So when they're carbon groups, we call them alkyl groups. These are carbon atoms that are attached to the carbon chain. When we name these, we will call these carbon groups with a YL ending. So if it's, for example, a CH3 group that's sticking up, well, one carbon is called methyl. Remember, methane is what we would have called it if it was by itself, but now it's a group on a bigger chain, so it's a methyl. If we had a CH2CH3 group, on a bigger molecule, this is a 2-carbon group, which we would have named as ethane if it was on its own. This would become ethyl. So a methyl and an ethyl and a propyl and a butyl group. And then we would name the rest of this could be, well, you'll see. They could be halogen substituents. Halogens are, again, fluoro, chlorobromine, iodine, the halogens. When we name those, we change their ending to be an O ending. So fluorine would just be fluoro. Chlorine would be chloro. Now, when they are substituents, we'll have to give you an example here in a second. These are what those substituents look like. So a methyl group is a CH3 that's attached to, let's say, a bigger molecule. This is a hexane. So right here in the middle, I'm going to stick a CH3 on it. So this would become methyl hexane. Now, this would also be 1, 2, 3, 4, 5, 6. This would also be methyl hexane, and you'll notice that they are both different. So there has to be something more. In fact, this becomes 2-methyl hexane, and this one becomes 3-methyl hexane, but we'll get there. But methyl, because the CH3 group is the substituent, and then hexane, because this is a hexane molecule. Ethyl has a 2-carbon group. Propyl has a 3-carbon group. Once we get to 3 carbons, we have isomers. So there's another way of actually attaching 3 carbons. We can attach them like a chain, but we can also attach them in the middle, and we call that isopropyl. So there's propyl and isopropyl. When butyl comes around, 4 carbons, we can attach them in a long chain. We can attach them as a chain of 3 with a branch. We can attach them, we can attach it kind of like on the second carbon of a chain. So this is attaching over here to the first carbon of the chain, but here we would attach to the second carbon of the chain, hence sec butyl. And then there's even a tert butyl option, where the whole group that we've attached is a butane, but it isn't a butane that we've seen before. It's basically the it's the isomer we saw at the beginning of this section, a butane where we have that branch. Tert and sec here you can get from how many carbons the carbon is attached to. So this carbon that we're like attaching to here on our bigger molecule, it's only attached to 2 other carbons directly, hence sec butyl, whereas this carbon that we're attaching has 1, 2, 3 carbons attached directly, hence tert butyl. That's where those names come from. You only just need to memorize which is which. You don't have to worry about differentiating these or drawing these, but if you memorize which is which, then you shouldn't have any problem spotting isobutyl from tert-butyl. And then again, some halogens, fluoro, chloro, bromo, iodo. So give this one a shot. Notice how many carbons it has. Notice that there are some substituents on it. Try to do your best to give this one a name. Now, I think we should probably work this one together, just so I can point out one of the things we haven't gone over yet, the numbering system. So, of course, longest carbon chain, there's 5. So this is pentane. Now, on pentane, we've got 2 groups, 2 substituents. We see that one of them is a chloro, and one of them is a methyl. So we need to give the name either something chloro, something methyl pentane, or something methyl, something chloropentane. So what we want to do first is number these carbons. We always want to number from the side that will get us to a substituent sooner. So if I number going this way, 1, 2, 3, 4, 5, I get chloro as 2 and methyl as 3. If I had tried to number the other direction, 1, 2, 3, 4, 5, I would have had 3 methyl and 4 chloro. So the numbers 3 and 4 and the numbers 2 and 3 will give you the correct numbering system. Basically, we want to number in the way that everything has lower numbers. So 2 and 3 is lower than 3 and 4. So we're not going to number from right to left. We're going to number from left to right. So now that we've done that, we don't want to say, well, we are going to say 2 chloro, 3 methyl, but we don't want to say it just because the 2 is in front of the 3. We're going to go alphabetically. So in alphabetical order, chloro comes before methyl. So 2 chloro, 3 methyl pentane. This name tells you how many carbons are in the chain, which carbons have substituents, and what those substituents are. If you had said 3 methyl, 2 chloropentane, somebody would have drawn the same structure, but you would have gotten it incorrect in that you didn't alphabetize your substituents. So, naming cycloalkanes with substituents is just the same. When one substituent is added to a carbon atom in a cycloalkane, the name of the substituent is placed in front of the cycloalkane name. There's no number needed because we'll always just count wherever the substituent is as the number 1. It really doesn't matter where you stick the group, right? Even if I told you this was cyclopentane, and I have 2 cyclopentanes here, right? And for some reason I have them numbered. If I draw 1 methyl cyclopentane, or if I draw 2 methyl cyclopentane, or if I draw 5 methyl cyclopentane, I always get the same drawing. It's always a cyclopentane with a methyl on it. So there's no need or reason to number. So this guy right here would be ethyl cyclohexane. Because it has 6, 1, 2, 3, 4, 5, 6 carbons in it. Ethyl cyclohexane. Haloalkanes. Haloalkanes are halogen atoms that replace a hydrogen atom. So these are named by putting the substituent, again, in alphabetical order. Have the halo group numbered according to the carbon where it's attached on the alkane. So here we have just chloromethane. It's just, there's no number here. Methane's a 1-carbon molecule. Here we have bromoethane. Again, there's no right or wrong place to put the bromo. It doesn't matter which carbon we put it on. We will always get the same molecule. Now with fluoropropane, there's a difference there. Fluoropropane, there is more options where we could put that fluorine. It could go in the middle, like it is here, which would be 2-fluoro. But we could also have put it as one of the hydrogens on the end. So this would have been CH2 with an F. This would have been 1-fluoropropane, not 3. This isn't 1, 2, 3, right? We would have numbered it as 1, 2, 3. We always want to get the substituent on the lower number first. So that would have been 1-fluoropropane. Here we've got a couple of substituents, right? Where's the longest chain here? Well, the longest chain is still 3. 3 carbons long. So on the number 2 carbon here, we've got 2 groups. We've got a chloro and a methyl. So chloro comes before methyl, 2-chloro, 2-methyl. I need to let my cats out of this room. Go, get out. Sorry about that. Cats follow me around everywhere I go. Drawing line angle formulas. So, let's draw the condensed structural formula and line angle formula for 2,3-dimethyl butane. So first thing you need to do is draw the main chain for the condensed structure. If I was doing line angle, that's easy. Well, it should have been prettier looking than that, but there we go. My line angle. Now the naming. This says that it's 2,3-dimethyl. So that tells me on my 2 and my 3, I'm going to have methyl groups. So on the 2 here, we'll go CH3. And this 2 here will go CH3. On my line angle, that just looks like lines. Those are CH3s. Now my line angle's done because the hydrogens are already implied. We got to go finish putting in hydrogens on the other side though. So on the ends, we've got CH3s. And these guys would normally be CH2s, but because they have branches on them and they can only have 4 bonds, these are now CHs. So there we go. Let's have you guys try one. So draw the condensed structural and line angle formula for 3-bromo, 1-chlorobutane. So give it a shot. So I've put in some help for you there. So you get your 4. So 3-bromo, 1-chloro. And you should have your you should have the right number of H's, right? Always make sure that there's not more than 4 bonds on any particular carbon. All right. Got a couple more for you. Try to name these. So drawing is one thing, naming is another. I think naming's easier, but doing practice on both will get you good at both. So go ahead and give this one a shot. All right. So very, very quickly, 1, 2, 3, 4, 5, right? You can see that that is 5 carbons long. Of course, you can go through each of these slides. I just want to get to the end here. Okay, so we've got 5 carbons, so it's pentane. On the 2 carbon, we've got a chloro, so 2-chloropentane. This one was a little trickier. Also had 5 carbons. Longest chain was 5 carbons. Even if you didn't happen to draw these exact pictures, as long as all the parts are there, I guess what I mean is, here we were naming, sometimes when you're drawing these, the substituents are shown as those two particular groups, but any two groups could have actually been, like, there's no reason that this couldn't be the group and this be the number 1 carbon. Okay, so that's just kind of random, but you've got 2-methyl, 3-methyl, right? 2,3-dimethyl pentane. Yeah, whenever I give you these that have some explanation, I expect you guys to go through the explanation when you're looking at that, and not just jump to the answer. Really work these out, and you'll benefit the most from this practice. All right, let's talk about some properties of alkanes. Now, the difference in uses of many alkanes actually results from their physical properties, and that includes their solubility and densities. So the solid alkanes that make up like waxy coatings on fruits and vegetables maintain moisture, inhibit mold, enhance the appearance. So we're going to talk about differences in alkanes properties. Now the learning goal for this section would be just to be able to identify the property of an alkane and to write a balanced chemical equation for combustion. So here, uses of alkanes. Alkanes with 1 to 4 carbons are gases at room temp. I guess I should say 1 to 4 carbons. So this is methane, ethane, propane, butane. These are widely used as heating fuels. Alkanes with 5 to 8 carbons. These are highly volatile liquids at room temperature. Volatile means that they evaporate easily. And so they're liquids. And they also are useful as fuels. This is pentane, hexane, heptane, octane. Good fuels. 9 to 17 carbons. These are liquids, but they have slightly higher boiling points. And they're found in motor oils, mineral oil, kerosene, diesel, jet fuel. This is a decane shown here. So again, fuels, they all burn if you haven't figured that out. Now, alkanes with 18 or more carbons are known as paraffins. These are waxy solids. Waxy solids at room temps of petroleum jelly, like Vaseline. Semi-solid mixture of hydrocarbons that have more than 25 atoms. So 25 atoms, definitely above the 18, just gives you that sort of solid, waxy texture and type of material. In general, alkanes have the lowest melting points and boiling points of the organic compounds. So, lowest melting and boiling points of all organic compounds. They only contain non-polar bonds, usually just carbon and hydrogen atoms. So non-polar carbon-carbon and non-polar carbon-hydrogen bonds. And they have very weak dispersion forces. This is those intermolecular forces we were talking about. And when they have these weak forces in solid and liquid states, it makes them really easy to melt. It makes them really easy to evaporate. Now, as the chains get longer, as the number of carbon atoms increases, the boiling point and the melting points go up, okay? And this is because longer chains have more dispersion forces. I mean, they're all weak forces, but if I have two carbons in a molecule and a bunch of two carbon molecules, there's not a whole lot of forces that are in between them. But if I have a lot of 25 carbon molecules, there's a lot more atoms to interact. The force, even weak, starts to add up. So longer chains will have more dispersion force. Let's talk about, you can kind of see a comparison here. So methane, ethane, propane, butane, pentane, boiling point, just to get this from going from a liquid to a gas, right? 36 degrees to get liquid pentane into a gas, but it only takes negative 164 for liquid methane to go to a gas. So you can see that increasing boiling point. Now let's compare that with branched alkanes. Now branched alkanes have lower boiling points than straight ones. Branched are lower MP and BP than straight chain. This is because they're more compact, so it reduces the points of contact between the molecules. If we had, I guess I could have used butane. Here we have hexane. If I have two hexanes, even if they're not lined up over each other properly, there's a lot of area of overlap, right? They can kind of like is it Pringles? Kind of like Pringles. They can get close to each other, or spoons. But if I have a mixture of butanes or hexanes where my hexanes are branched, this is a hexane as well, or a 6-carbon molecule. This guy can't pack as close to this guy. It's more compact, the shape's different, so we don't get as many points of interaction. So that's what we're talking about here. So because they don't have linear shapes, they can't line up close to each other, branched alkanes will have lower boiling points and lower melting points than their regular counterparts. So here, all three of these compounds have 6 carbons in them. You can see the straight chain is 69. Add a branch, now it's 63. Add 2 branches, now it's down to 58. So that's how the physical property changes with the branching. Now, cycloalkanes, which I've included on this table here, actually have higher boiling points than the straight chains. This is because they have limited rotation on the carbon bonds. They maintain their rigid structure, and they can actually stack pretty closely together. So cycloalkanes are more like Pringles. They can stack and they can orient themselves, get close together, and make points of contact. And so we'll see their boiling point kind of up from the same number of carbon boiling points that we saw go down with branch chains. So here, these are cyclopentanes. So comparing that to a straight chain pentane, 36, our number goes down when we add branches, but it goes up again when we make it cyclic. Hopefully that wasn't confusing. Now we need to talk about the combustion of alkanes. So the carbon-carbon bond, right, in alkanes, difficult to break, which makes them really good at making long chains. But alkanes do readily burn in oxygen to produce carbon dioxide, water, and to free up some energy. This is why they are good fuels. So what we need to be able to do is write a balanced equation for that combustion. So methane. Methane is natural gas that we use to cook our food. It's CH4. Now, again, when we are writing equations for combustion, we usually show its phase. We always have to react it with oxygen, and that's molecular oxygen or gas phase oxygen. We usually have to put in some sort of energy to get it going. And then our products are always carbon dioxide, gas, and we'll end up with some water, also gas. I mentioned energy. Energy gets freed up as well. Propane, same thing. Propane is a little bit bigger of a molecule. Excuse me. 3 carbon atoms. Propane is used in portable heaters, gas barbecues, that kind of thing. Methane comes out of methane's our natural gas. Propane we use more industrially or commercially. Both of these have the same ingredients for combustion, but balancing, right? Balancing is writing or making sure the number of atoms are the same all the way around. So for methane, let's do methane first. We've got one carbon atom in methane. Hey, there's one carbon atom in carbon dioxide. That works out. There's 2 hydrogen atoms in water. But there was 4 hydrogen atoms in methane. So right off the bat, we're going to end up needing 2 water molecules to form so that we know where all of our hydrogens went. That ends up causing 2 oxygens from the water and 2 oxygens from the carbon dioxide to be products. So we have 4 oxygens altogether, the 2 right here and the 2 in the waters. So 4 oxygens are consumed in this reaction. So we need to make sure 4 oxygens get consumed. And the way we do that is put a 2 in front. 2 in front of the O2. So now there's 4 oxygens being used. All of the atoms check out. You try it for propane. It's a little bit harder. Let me help a little bit by writing you a formula for propane. It's C3, so C3H8. But you look at it the same way. You say, oh, look, there's 1 carbon in my carbon dioxide, but there's 3 in propane. So I have to have at least 3 carbon dioxides then. There needs to be conservation of those 3 carbons. There's 8 hydrogens in propane. So there needs to be 8 hydrogens produced. Sounds like 4 water molecules. 3 times 2 is 6 plus 4 is 10. 10 oxygen atoms show up in our products. So we need 10 oxygen atoms in our reactant. 10 would be 5 of these O2 molecules. And that would be a balanced equation. So again, this is something that you should know how to do already from Chem 20 or from Gen Chem, whatever prereq you took for this class, but you might want to review that. We're just about halfway through this chapter. We'll stop for this first part of it when we get to the alkenes. So I think we've got 1 or 2 more slides here. Let's talk about the solubility and density of alkanes. Now, alkanes are nonpolar. We saw that. This water is polar, so what that means is alkanes are insoluble in water. You're looking at an oil spill, by the way, in this picture. Alkanes are also less dense than water. So if we mix them together, they're going to form a layer on the top of water. Alkanes are flammable in air. So they will ignite. And alkanes are also found in crude oil. When we find crude, we actually distill it. We run it through a series of boiling to get off all the lower boiling point alkanes. All the gases come off first, all the liquids come off second. Ultimately, we end up with something that we can refine and use for the higher and higher quality fuels like jet fuel, and then ultimately we get like tar and asphalt type materials. But all of the low melting point, low boiling point alkanes that we looked at, 1 through 10 carbons, 1 through 20 carbons really, will come out of oil. Oil spills are no fun. Because of those physical properties, right, the fact that they don't mix and that water is more dense, oil will float. And so back in April 2010, as you can see here, there was an accident and a lot of oil was spilled. Now, there's a few ways that we try to clean that up now. There's mechanical ways like scooping up the oil and trying to just get it off the top of the water. There's chemical ways using materials that'll attract the water and then again picking them up, scraping them off the top of the water. The newest ways, microbiological, we're sort of manipulating bacteria to be able to eat the oil. And that makes it, this works with plastics too. We've got bacteria now that can eat a plastic bag, in something like a day, which is pretty neat. And so we're working on all of these different ways to kind of clean up our own messes. But this is and continues to be a problem. If we spilled oil and it sank to the bottom, who cares? The fact that it floats on the surface, though, right? Birds get in it, animals get in it. It gets all over our shores. I mean, it's not a good thing. All right, learning check. I think this is it. So give this one a shot. Balance this equation. I'll give you some hints again. Remember, this is your molecule. You need O2. You're going to form CO2. You're going to form water. So go ahead and give that one a shot, balancing. And then hopefully you came up with something like this. This was a little bit of a tougher one, right? Because you had to use an odd number. Well, no, that's not true. You had to double the amount of butane in order to make it work. With 1 mole of butane, you would have needed 6.5 O2s. And that doesn't make any sense. You can't have a half of an O2 molecule. So if you double everything, you get rid of having to look for 6.5 O2s, right? You just make it 13 O2s. So that's why everything got doubled here. Okay. Yeah, we're going to break this video into 2 parts. So this is going to be a 2-part chapter 12 lecture. So when we come back in the second video, we'll do alkenes and alkynes. All right, see you then.